So let's pick up where we left off. Last video, we calculated that the Galois group of this polynomial was isomorphic to S3. Now what I want to do is do a little bit of a dive into the structure of S3, some of which we kind of know how S3 works. We have a fair bit of experience with it. So let's take a look at it and see if we can pick it apart and kind of remember what the subgroup structure of S3 is. The first thing that we know is that by Lagrange's theorem, the order of a subgroup divides the order of the group. And S3 has order 6. So what we should do then is we should look at the groups whose orders divide 6. This is luckily not so bad. For order 6 itself, you have the whole group, because of course. Then we can ask, what are the order 3 subgroups? For order 3 subgroups, there's only one. It's the subgroup, because it has to be a cyclic group since it's a prime order. And so this is the group generated by our order 3 element. That's the same thing as being generated by its square, but that's all we got. For order 2 subgroups, these are also cyclic groups. These have to be generated by some kind of transposition. And so we know one such transposition, namely tau. And then for other possibilities, well, we have to figure out what are the other transpositions in this description of S3. And so the simplest way of doing that that's standing out to me is to try to calculate something about what the other compositions could possibly be. I can think of actually two ways of doing this. The first way is we could figure out the isomorphism, since I know that this is a 3 cycle and this is a 2 cycle. I could try to make an isomorphism S3 and our Galois group, perhaps by sending sigma to a 3 cycle and tau to a transposition of my choice, like say this one here. And then we could check if this defines an isomorphism. Like, for example, can I generate everything? In order to check if this is an isomorphism, I'd have to work with sigma and tau a little bit more anyway. So I think it makes some amount of sense to convince ourselves, for example, that sigma squared tau sigma tau and sigma squared tau are also order 2. In other words, I have to calculate that sigma tau squared is the identity function, and similarly for sigma squared tau. I think I'll just do it for sigma tau because sigma squared tau will be very, very similar. And the best way to do that is to use our description of sigma and tau that we gave up here. Let's see if we can copy this over. Haha. Let's grab this and bring it down here where we can look at it. That's not where it's supposed to go. We are grabbing you and putting you down here. Hey, why are you being difficult? Okay. Yeah, in case you guys haven't figured it out yet, I don't really know anything about how to use OneNote or if there's a better way of doing this. But in any case, here's our description. And we can now figure out what happens with sigma and tau by calculating using these things, right? We can calculate what sigma tau squared does to the square root of 3i, and we can calculate what it does to the cube root of 2. And we know that this guy individually fixes this guy. This guy individually fixes this guy. And so we just want to know, like, what does sigma tau do and what does sigma tau squared do? So off the bat, we know that 1 goes to 1 because it fixes both of them. What happens to the square root of 3i? Let's come over here and calculate it. So sigma tau of the square root of 3i. Well, tau is complex conjugation, so this becomes minus the square root of 3i. The minus sign comes out because sigma is a field automorphism and it respects multiplication by -1. And sigma fixes the square root of 3i. So this gives me minus the square root of 3i. Okay, we don't need this anymore, but we do need space, so I'm going to erase it. Let's continue to use that little chunk of the board as our scratch workspace. And now let's see what happens when I apply the same thing to the cube root of 2. So sigma tau applied to the cube root of 2. Tau fixes the cube root of 2. Sigma multiplies it by omega 3. Sorry, that's not how you write an omega. Omega 3 cube root of 2. So by itself, sigma tau are kind of doing the things that you expect them to do, right? Each of them affected one of these things. So now they're both affected. Well, the question then becomes, what happens if I do this process twice? So let's try it. Let's try sigma tau squared. Again, we know that 1 goes to 1 because it's always fixed. And now, square root of 3i is evidently sent to its negative, and then this part is sent to its negative, and the negative of the negative gets me back to where I started. So therefore, square root of 3i goes to square root of 3i. The question becomes, what happens to omega 3 times the cube root of 2? So for this, we see that the first time, the cube root of 2 is sent to omega 3 times the cube root of 2. Now I have to plug this in again. And here it's not quite as simple because we know that tau is complex conjugation, but also these things are field automorphisms, right? So they break up over multiplication, and this gets me sigma of tau of omega 3, tau of the cube root of 2. Which in turn, tau of the cube of omega 3, being complex conjugation, is omega 3 squared. We saw that already. Tau leaves the cube root of 2 as it is. So we end up here. Now I want to apply sigma, and sigma sends the square root of 3i stuff to itself. And we remember omega 3 is equal to minus 1/2 plus square root of 3 over 2i. And omega 3 squared is the same thing as the complex conjugate. And so since sigma respects the square root of 3i, sigma respects omega 3 squared. Still breaks up, right, into sigma of omega 3 squared, sigma of the cube root of 2, but this part just stays the same as omega 3 squared. On the other hand, sigma of the cube root of 2 picks up another omega 3. And now we have 3 omega 3s, which is of course 1. And so what we see is the cube root of 2 is mapped to itself. I don't think that's super duper obvious, right? I think you, like, naively, one might expect that this would be omega 3 squared. But it's not how this shakes out, because this is a field automorphism. It's not just a linear map. A little bit easy to forget exactly what structures are at work. Okay, so that proves that sigma tau is a transposition, right? It's an order 2 thing. And so since we've checked that this works, you guys will readily believe that a similar computation works for sigma squared tau. And so the only thing left to do, really, to complete our classification of the subgroups is to include the order 1 guys, but that's just E, right? So we'll just sneak him in there. It's kind of fine. Okay, so we've seen what all of the subgroups of S3 are, and we've seen how they manifest themselves in the Galois group. Now I will tell you the main theorem of Galois theory. This is the so-called Galois correspondence. And what it says is that subgroups of a Galois group are in bijection with how do I say this? With intermediary fields. K, we'll call them maybe F, Q, right? Fields that are possibly in between K and Q, where every subgroup of automorphisms fixes an intermediary field. So in other words, for each of these subgroups, there is a field of things that they fix. And we can see that. Like, for example, for sigma here, we can see sigma fixes the intermediary field that is generated by square root of 3i over q. Whereas tau fixes the stuff generated by the cube root of 2. And what the correspondence says is the same is going to be true for any possible subgroup that you can spot. There will be some fixed field in the middle. And because they are in exact bijection, they'll come in the same number. But moreover, this bijection is order reversing. In other words, the bigger the subgroup, the smaller the fixed field. And that should make some amount of sense too, right? Because if I look at a small subgroup, a very small number of automorphisms, then what they fix is going to be relatively unconstrained. But if I have a lot of automorphisms, then the different automorphisms are all moving around different things. The only thing they can fix is sort of like their common intersection. And so there won't be as much stuff that's fixed. So the closer you get to the base field, the bigger the group. And or alternatively, the bigger the field, the smaller the subgroup in question. And so we may recall that we had a lattice theorem for groups that said if you wanted to investigate subgroups, you could organize them sort of from, I'm going to say least to greatest in air quotes, by making a sort of diagram and organizing them by inclusion. We can do that with S3, and there's not that many groups, so it's not that hard, right? So for S3, what's the situation? We have S3 up top. We know that S3 contains a couple of order 3 groups. We wrote them down up above. Sorry, not a couple of order 3 groups, a couple of order 2 groups. We have just the group generated by sigma for order 3. And then we have tau, sigma squared tau for order 2 groups. And all of those contain the identity group E. So now what I want to do is like investigate just a little bit closer the automorphisms that we have been understanding in our Galois group and their fixed fields, right? Because we can just as easily change this S3 to, right, gal KQ, right, where K is our specific group. And now let's take a look at the fixed fields. Well, sigma, we said fixes square root of 3i. So we could write that the fixed field of sigma is generated by square root of 3i. The fixed field of tau is q adjoin the cube root of 2. And did we work out the fixed field of sigma tau? We did not. The question is, what is the fixed field of these things? Okay, well, sigma tau squared is the identity. So the question is, what's the fixed field of sigma tau? I didn't work this out in advance. This was a little bit of a mistake on my part, but that's okay. We can just think about this a little bit. We know that sigma tau does this to the generators. So basically what we should do is we should look to see if we can spot a combination of these that we can then check will be preserved. And it's clearly not going to work with omega 3 by itself. So I want to try omega 3 squared. Yeah, let's try sigma tau of omega 3 squared times the cube root of 2. This is sigma, and then we have tau of omega 3 squared, tau of the cube root of 2. Tau is complex conjugation. We already saw that that gets us back to omega 3, right? Because complex conjugation is an involution. And this thing fixes itself, right? Tau fixes that already. And then sigma of omega 3, what did that one do? I forgot. Sigma fixes omega 3 because it fixes the 1/2 and the square root of 3 over 2, the square root of 3i individually. So that part gets me an omega 3. And the cube root of 2 then was picking up an omega 3. It was our definition. So this is in that, yeah, that works, right? We get back to what we wanted. Okay. So what that means is this thing generates the fixed field of sigma tau. Slightly complicated expression. My bad for not being a little bit more on the ball with this. So in any case, now we are able to assemble the fixed fields. And let's try to compare them a little bit, right? Let's see if we can put these side by side. So here we have the subgroup structure. Now let's look at the fixed fields. Well, on one extreme is we have the whole field, right? This is just the original K. The only thing fixing this is the identity function. So maybe I should put this at the bottom, right? The trivial subgroup with the identity function fixes the whole K. Going up and looking at our intermediary guys, sigma's fixed field is this Q adjoin square root of 3i. And I'm going to intentionally kind of try to draw the picture sort of upside down. Square root of 3i. We worked out tau's fixed field. Tau's fixed field has the cube root of 2. And then I worked out sigma tau, and then I guess I didn't work out sigma squared tau. But we just saw that the fixed field for sigma tau was Q adjoin omega 3 squared cube root of 2. I'm sorry, I'm really hurting for space here. I should have left more room to draw this bigger. That leaves the sigma squared tau guy. The fixed field of sigma squared tau, well, the calculation is basically the same. You guys will believe that since this one had the omega 3 squared, this one gets an omega 3 by itself. And then all of these things on top, right? The full Galois group fixes only Q, right? So in other words, I'm realizing that what I'm writing is a little bit on top of itself. What are we seeing here? We're seeing the Tower law in the sense of we know that the degree of this over this is 6. And look at the individual degrees here. This thing is degree 2. These are degree 3. These are degree 2. This is 3. They multiply to 6. In the same way, this is order 3, right? And so therefore has index 2. And so you see in each case, it is exactly reversed from the other. And so that these diagrams are upside down from each other is what this theorem asserts. That in other words, you can understand the structure of all intermediary fields using the structure of the Galois group of the big field. Okay, I've been talking now for 20 minutes again. that's what I wanted to show you. I think the thing to do is practice that, continue to work with this, right? To continue to see different subgroups of Galois groups and also sort of what these intermediary fields can look like. And so what I'm going to do is pick out a bunch of problems for you guys to look at to practice. And then I think we will be ready to call it. All right. See you soon. Take care.